Hello, everybody. It's very good to see you here to our workshop, EuROBIN Mapping the Future of the Generative AI. I'm Rebecca Schedel-Wartrup from DLR, and my co-chair here is Passant Lagrui.
Yeah.
Okay, I will introduce euROBIN. Yeah, we have a network of excellence for robotics and AI network. The coordinator is Aline Albuschäfer. We have 31 partners from 14 countries. Okay. We have a lot of robots in our community, and they are really some of the coolest on the planet. And we seek to boost our skills and their skills of the robots to new levels. And we want to learn and benefit from each other and boost our transferability and reusability of these results. For that, we create EuroCore. It's a repository. And we do the first steps to act GPT, not chat. For robots, we act. Robots is about acting, no chatting. And we will we are filling right now EuroCore repository with the data. And we will have a euROBIN event end of this year in North Sea, and we will fill a lot more. We creating joint interfaces, data structures. We are preparing the work on joint generative AI model, and we have the lead position of the robotics, and we want to go further.
So just a bit of context why we're doing this again just after the highlights. The session is organized by HumanE-AI and EU for Urban, and we wanted to highlight the Gen AI stuff that are happening in both networks. For HumanE-AI, as Paul already said, we're doing collaborative human AI intelligence, and we're focusing on augmenting the human capabilities. Okay, you're seeing that now. So we focused on creating new generative AI bundles, research bundles, and we created 4 platforms in HumanE-AI, and we wanted to tell you about that in case someone wants to use them or collaborate on further developing them. The first one is we created the first platform for evaluating human-AI collaboration through different tasks. The second one is we created an ethical assessment AI-based platform where you can plug it, and then it evaluates how the ethics of a particular solution is working. The third one, we created an educational platform with LLMs using chatbots. And the last one is we created a chatbot for interacting with AI on demand. There's a bit of delay with the slides, but... So why are we doing this session in the first place? As Cecile already said, there's a lot of business value at the moment in Gen AI, estimated between 2.4 to 4 trillion euro per year. And the current key players are actually in the USA, and we have a need to have Gen AI that has European values. There's going to be 4 billion euro EU investments, as Cecile has said. There's a lot of details about the funding. I just thought to highlight the 2 things I think are most relevant to the community here. The first one is the 500 million euros for Gen AI for Europe, and this is going to be about use cases. And the second one is the 2.1 billion euros about AI factories and supercomputing services. So what are we going to do today in terms of an agenda? The session is divided into 2 parts. The first part is a vision 1. We will have 4 keynote speakers telling us what are the core research challenges for Gen AI in Europe. If they have the money, what would they be doing with it? And the second part is we're going to turn to you for some feedback. What would you do if you have the funds? Our speakers are going to be Paul, and he's going to talk about, Paul Kovic, he's going to talk about grounding Gen AI in real world. Michael is going to tell us how to give robots some cognition. Rudolf is going to tell us the perception algorithms using Gen AI for robots. And John is going to tell us about how to do collaborative human-centric Gen AI. Without further ado, we start the session.
Okay, our first speaker is Paul. He is from DAE, and yeah, it's your floor.
Okay. Yeah, so happy to be here. I'm talking about multimodality of grounding Gen AI. And just to explain what I mean, I really want to go a bit to the basic and look what is really the core of Gen AI behind the hype. And going to the basic, I really want to go back really to the basic, very fitting here to Greek philosophers, right? Some of you may know this Plato's analogy of the cave that say the limits on human perception are that the way humans perceive reality is like those prisoners sitting in the cave, where all they see are the shadows from outside, which can be the shadows of reality, but can also be the shadow of something that they think they see or that somebody else was projecting. So perceiving and still struggling to understand that realities, human invented language to talk about the way they perceive visual reality and to record that. And having invented language and talked a lot about reality, they wrote books. And then at a certain stage, we took books and digitized them. And at a certain stage, we took those digitized texts, put them into neural networks, and created probability distributions over the lexical tokens in those digitized texts. And now, that of course are LLMs. And we're all surprised how this probability distribution led to systems that actually had complex text that make sense, become most probable, and could answer questions. How those probability distributions became things that I think in the end are the first time in history of AI really comprehensive world models. They are noisy, they are approximate, they are comprehensive. And for me, that is behind all the hype that we can build on top of it, the real core of Gen AI, or actual foundational models. And then, of course, today we don't just talk, we post, right? So now we have posts that contain text, but also video. And the trend is that people now put those two together, create joint probability distribution, and what you then have is actually a system that, based on that world model, can relate to each other things that come from vision, things that come from text, pictures, videos, text. And if you really go down to the basic, that is the mechanism of all the magic and hype of generative AI, right? It's a world model where you can actually relate different realities, modalities to each other. And on a technical level, we have this beautiful embeddings abstract representation. And that is the core of this multimodal and grounding, to which you can anchor all different other types of information and relate them beautifully to that world model. So why is it really relevant? We're talking about interactions with humans and HumanE-AI-Net, right? So that really, for the first time, give us truly intuitive, unobtrusive interaction based on natural causal speed, based on visual and audio cues. And let me show you an example. Some of you may have seen this beautiful Google demo on Project Gemini. Again, they are reading it, right? So you have a phone, you just walk around, and you tell the phone, do you see anything that could make sound, right? Something I could tell to a friend I'm walking around. And then you walk, and once the phone actually comes over a picture of a speaker, it outputs OSP speaker. It makes a sound, right? So you have using exactly this ability to link those representations in audio and video and in speech to our world model, currently an interaction with an AI like I would interact with a friend. And that, of course, is again deeply connected to this notion of common ground and shared perception, right? You get CI psychology. The reason I can talk to each other is not only because we exchange sound, but because those sound relates to our joint world model. And all of you know, if you try to work with a social scientist, with a doctor, it gets difficult because we have different world models to which we relate, right? So giving AI a world model that it shares is a fantastic and powerful thing. And how did Gen AI advance it? Let me show you something. So when I was talking about limits of AI, I used to show students this slide showing, yeah, we have speech recognition, but imagine the following situation. You have a couple sitting at a table, they ordered steak and salad. And the waiter comes and said, who has a steak and who has a salad? And the lady, not quite politically correct, maybe says, oh, I'm the rabbit, right? You immediately know what it means. You immediately know a lot of connotation with it. But I assumed like 5 years ago, no way a speech recognition system can deal with it. So, last year I put the thing into ChatGPT. What happens, man and woman sitting at the table, I get the perfect answer. Right? So actually, that is the thing, connecting to complex world models that you actually now have. And once you have this truly intuitive interaction and connecting to this common ground, shared perception, that is where our vision that we have in HumanE-AI-Net, connecting humans, enhancing human capabilities, that is where it becomes reality. One interesting point there is that actually something we sometimes consider to be a problem, right, with this analogy of the cave, that those systems are more rooted in the way we humans perceive the world rather than the real world, is actually an advantage because they talk to us. But it can also be a problem. And let me account the challenges and the problems. When we use GenAI to collaborate with us, to address problems, what we really want to have is a system that sort of let us get away from our being locked in the cave and actually see the world outside the cave, right? You want systems that, not like today's AI systems, enhance the building of echo chamber, enhance polarization, enhance misinformation. You want systems that help people both on individual and social level cope with, understand, and address the problem of our world, the complexity of our world, right? So we want to have an AI that actually is able, to help us connect to this real world. So how does today AI fare on this? And here's an example I love. Maybe new system changed it, but it was not so long ago, at ChatGPT-4, I put a question. Imagine you're doing push-up, but not like this on the ground, but on a steep side, like this. So you are in this position. Everybody knows that's the cheap way of cheating, right? Because that's easier to do. But I asked him, is it easier? Here's the answer I got. Of course it's more difficult, because any type of physical activity you do uphill is more difficult, right? It reflects the notion those things are rooted in probability distribution of lexical tokens without an underlying model of reality. And that is where it comes and mean in grounding those things actually in reality. That's physical reality. You can do a similar thing on social reality. So if you look at this, that today's GenAI is not as much taking us outside the cave, it's one of the prisoners in the cave. And that is what we mean and what we want to change by saying we want to do grounding. So yes, we want to retain the process that you have here, that we generate our probability distribution, our models, by looking at the way humans perceive the world. But on the way, we want to make sure that that creation is inserted, it has inserted some knowledge about how the world really is. That it is connected to the world as it is physically, but also to the social world. And it's a grounding problem. And if you come from core AI, of course, grounding is one of the problems that we have with us in AI since 50 years. And that problem remains and gets even more grave in a way in GenAI, because we do have this world model and it's sort of grounded, but so indirectly through this cave chain of things that we need to improve it. And for me, that is a really, really major challenge that generative AI is facing, especially if we are looking at it from the point of view of the European vision of trustworthy, reliable, transparent AI. So how do we do it? What are the challenges, right? So first of all, we of course need to be able to include in the training of those models, not just purely lexical tokens, but knowledge. There are approaches to it, knowledge graph, ontologies, other things, but it's an open problem in which you need to invest. The other problem is really connecting those data-driven ways of deriving models to physical and social models, right? A lot of these things, like we talk about this exercises, right? If the system had some sort of an understanding of the model of physics and that was connected to the data-driven thing, that would be interesting. There's a way to do it, right? Physically informed neural networks, other stuff. How do you insert that into model training? An open problem. One thing that we have been very strongly pushing is you should really try to connect models to simulations. A lot of stuff that you do can actually be verified through simulations. Models are really good at producing code. Well, not producing code, but producing sort of something related to code, translating stuff. So I will connect them to simulation and let them actually extract the data here. Can we use simulation to generate synthetic data? And then, of course, very important multimodality, text and vision are one. But there are many, many other modalities. We need to leverage them. We need to include them. That was what Cecile was talking about, this new call. about multimodal models. We need to connect those things to the model because many of those modalities are more directly coupled into the physical reality. And I believe that we need to break through the current cycle of very, very strict, like pre-training, refining, go to the back, pre-train again while they're obsolete. Have models that can improve actually through the interaction with the world, through interaction with humans, through interaction with simulations. And to finish, let me just look again at this point here that we have on leveraging other sources of information, right? Again, if you look at reality outside the cave, today it's just people looking. Our reality is digital. We have Internet of Things, sensors, input devices. Most of them are online all the time. These are the sources of information that we should be leveraging. And the important thing is that the Internet of Things, those sources of information, are things that are strategically highly important for Europe. In some of the things, if you look at social media and other stuff, you may argue it's actually dominated by Google, Facebook, and so on. But when it comes to manufacturing, smart manufacturing, automotive, smart cities, sustainability, these are all topics where Europe strives to dominate and still has an edge. These are all topics that are strategically hugely important for Europe. And these are all topics that are very closely connected to Internet of Things and to data that is the Internet of Things. So if you want to build models that can help us in Europe with those strategically important things, then these models need to seamlessly include information from this truly multimodal sources of information. Internet of Things is an extremely important aspect. And you can say, oh, there are multimodal models. So let me give you an example. If you're into multimodal models, you know CLIP, one of the first combined vision text models. They did a version once that includes IMU, very common sensors. The problem is, if you look at it, they have 500 million image caption pairs on which are trained, and something like 200 hours of sensor data. And that is something that goes throughout. Another very well-known current work, you may know ImageBind, that actually sort of reverses the whole thing, goes from image and bind text. They claim to be multimodal, but the sensor they have is essentially everything vision-derived. Depth cameras, thermal cameras, right? Important, but it's not true multimodality with sensors. And when they come to sensors, they have a few hundred or couple of hours. So what we need to do, the future challenge, is to go from these models that are like vision and text and sort of alibi maybe a sensor here and there, to models where these new sensing modalities are on equal pairing, where the embeddings and the latent space of those new sensors are aligned with vision and text, as well as today vision and text are aligned to each other. And also benefit robotics, many other things. So what do we need to do? Of course, the problem are data sets where you have synchronization between text, vision, and all the sensing modalities. You have the problem, and I believe that's the solution. What we need to do is actually creating high-quality simulation-based synthetic data sets. The problem there is really input-thread variability, right? An image is an image. It can have different resolution, it can be turned, but sort of you can transform them. You look sensors that are, I don't know, pressure sensor on the ground, IMUs on the body, vibration sensor in machines. How do you bring those together? How do you bring them together to train one model? How do you deal with streams of those things, right? So that's a whole new research question. How do you think with complex spatial temporal information? You look at smart cities, you look in the environment, very, very important aspect. Then there is a scaling. We have to manage AI and edge. How do you take these models and actually put them on small devices? And if you run on small devices, can they collaborate? Can you go to things like continual training, federated training, new training concepts, right? Those are all things that are absolutely crucial for this multimodal application. So coming to the key takeaways, what I want to tell you. First of all, I believe that one of the important things about GenAI is that it's the enabler for our vision of truly human-centric AI, when AI and humans collaborate. The problem is, if you really want this collaboration to be fruitful, as in allowing us to better deal with the problems of our world and society, that it can only happen if we manage to ground the models in reality, both physical and social. Because otherwise, they will just be enhancing our echo chambers and not going beyond what we have. And if we really want to do the grounding, then multimodality, true multimodality beyond vision language models is again the key. And it's a key not just to making this human AI collaboration good, but it's something that is absolutely central to let's say, the European strategy and things that are important for Europe to stay competitive, to address the issues that we want to address, right? And in a way, the thing about IoT is talking about robotics, and of course embodiment is important for intelligence, but this is sort of a parallel and complementary type of embodiment by sensing, controlling all of those Internet of Things things. And these are, I think, the four things that as Europe goes toward catching up and becoming a dominant power in GenAI, these are things that we need to address.
That was very interesting. Thank you, Paul. The next speaker is Michael Beeth from the University of Bremen. And the talk is about give robots cognition.
So thanks a lot for having me here. I will give the same talk, but only from a roboticist point of view. So as a roboticist, so I think one of the kind of very enlightening talks is that Dan Wolbert gave, and that was a question of why do we as humans and other animals have a brain, right? And he says we only have it for one reason, because we can move our body, and with our body we can change the world, and this is how we accomplish tasks, right? And even if you look at language, right, language is actually moving your tongue, and you're communicating to that. So that's kind of where intelligence comes from, and why do we have it, right? So, and I want to take the position for this talk, right? So we have intelligence for one reason, and one reason only, and that is to successfully act in the physical and in the social world. And this has very important implications, and I think that AI is not taking them seriously enough, right? Because if you have a system that acts in the world for a long time, that has really to be successful, that has to work with the open world, and we see that this is not easy because we are seeing in autonomous driving, right? So that kind of going that way is really tough. There is also another aspect, I think, that robotics brings to generative AI, right? And this is, many of these lessons are very old ones, and they are forgotten because of academic dementia. And so it's kind of this one, it says, if bridges had to be glitches, we wouldn't have a man-made bridge across the Golden Gate, because complex bridge building couldn't be understood, taught, and remembered. Successful engineering requires kind of idealizations and to successfully kind of gradually bigger models, right? And I think if we are looking at autonomous driving, if we want to have robots that act for a lifetime and that are basically helping humans, I think we have to understand them in an engineering way, right? And I think the question is how to bring these worlds together. And so the key problem, if you look into the world from a robotics point of view, is that you have to get these tasks that you have to, and they are typically very underspecified. They are tasks like set the table, and you have to find a specific body motion that achieves kind of the desired effects and avoids unwanted ones, right? And so kind of that single instruction, set the table, has to make that possible, right? And robotics has the tools, has the understanding to actually do that, and actually do that for different tasks in different environments with different robots. So if you look at some of the challenges in generative AI, like compositionality, generalizability, transferability, they are solved in robotics, right? The thing that you pay for in robotics in order to get these things is that you have to have very detailed models. And the question is, where do we get the models from? And I think generative AI, if we are looking at these kinds of technologies, we can basically scale that kind of thing to any environment, any domain, like ChatGPT does, if you basically load it with all the knowledge, right? So the key from the robotics point of view is you see that kind of behavior. The only thing that you get is set the table, and the rest has to be in the knowledge and reasoning of the robot, right? So the kind of how generative AI goes about it is we are looking at that at a huge probability distribution. We would want to have the situation, so that's exactly the kind of picture with a cave, right? We don't get it, so we have to substitute it by vision, language. We are doing videos, we will basically have computer games, we will have 3D models of the world, and we get all the data. What we have learned is that in that game, language is of key importance, right? So because language is stringing everything together, and somehow it's a very powerful kind of mechanism, and everything that humans have learned about anything is somehow as text available in the World Wide Web, right? And that's kind of why these things are actually working. So we are looking at getting all the data in and basically building data distributions just of successful examples. And then kind of the game is we are just looking if we want to do kind of these controlling of robots for complex tasks. We look at the best, the action or motion, the next motion segment with the highest expected utility with respect to kind of the, oh, wait, there's one thing you're like, do you want to, okay, yes, so I think that's fine, right? Yeah, so, yes, and I think kind of the picture in the upper left is it's kind of an old one, but I think it's extremely impressive, right? So if you are looking at the generative AI techniques and you ask them to generate a picture of salmon swimming upstream, and they generate something like that, how cool is it, right? So how realistic does it look? And it's doing exactly the right thing, right? It's generating the pictures with the highest probability if you look at all the pictures of salmons and all the pictures of swimming fish in the internet, right? The only thing is it's wrong, right? Because it's physically not possible. And this is kind of what is the problem, because we are only looking at the shadows in a cave and not on reality. We don't have the models about what is happening, and we don't test them, right? So also, if we are looking at long-term autonomy, right? So human brain looks different if it acts successfully in the world. But there's always branches of possible futures. We can basically do the next step to get flexibility, to improve our position and be more reliable in the future. And what is very important, if we are looking at the different causes of action, we can actually talk to another human about what these different options are, what the trade-offs are, why one should go one way or the other, and what would actually happen if we do that, right? So humans are capable of building these kind of representations of their intended actions before executing them. And I think that's kind of, if we are really looking at the next generation of generative AI systems, that's an important point, right? And nature, at least kind of according to some neuro and psychologists and whatever, they have the dual process theory of thinking fast and thinking fast, right? So they don't say that intelligence is just a matter of associations and kind of deriving from that. But there is a second system that watches what the first one is doing and actually steps in if problem. It does it maybe very seldomly, but it's the same kind of mechanism when OpenAI tells you to check the answer of to check the answer that they give and make sure that it's right, right? So it's kind of, it might be a mechanism that seldomly hits, but if you have agents that act in the world for a long time, it's essential, right? And if you're looking at that, if you are taking that actually robots are building kind of also models, and they can be latent ones that are incorporated in the generative AI model, right? You can kind of decompose the systems in understandable general parts that can be put together, that can be transferred, and you get all the mechanisms and the understanding of robotics that this system is actually producing collision-free parts, it's producing optimal parts. It can do it for any robot body that's possible, for any environment that you specify, right? So the question is, like a physicist, right? A physicist wouldn't give up Newton mechanics or the Navier-Stokes equation because of data-driven AI, right? So I think the question is how the fields grow together and how to leverage the understanding we have with the new opportunities. And I think the same way as physicists think about kind of what is the potential of bringing the fields together, the same applies for robotics, right? And I think this is where we have to go. Yeah, so I think where I see kind of a huge opportunity for foundation models and bringing it together with robotics, there are all places where basically these fields come together. So you can think about the system, the one I've shown, it's a kernel, right? And the other system, the learning system, only computes the input for these systems and the output. You can think about learning representations. You can think about learning the optimization functions, and there are huge opportunities of bringing that together. So we want to have kind of robots that actually can learn from the World Wide Web by watching videos. But unlike the way it's done only on combining the data, we would want to have robots that mentally simulate what they are seeing in the video with their mind's eye. And their mind's eye, right, it's also grounding their kind of foundation models with a kind of a concrete simulation. And if you run that simulation in a digital twin, it's constantly updated with reality over lifetime, and this is probably one of the biggest motors of it. In euROBIN, we basically try to go that way by trying to build a virtual research building, which is actually taking the physical labs, having digital twins of them, and basically giving everybody access through software containers to those systems. Those systems are actually represented as explicit models. They automatically kind of record their experimental data, they semantically annotate them, and we can use these data for learning kind of the generative AI models. So getting that together, I think, is a huge kind of chance and opportunity to put forward essentially the technology. Okay, so that's kind of my point of view as a roboticist for what opportunities we have here.
Thank you, Michael. It was very interesting. Yeah, a next talk also about robotics perception algorithm used generative AI. Here's Rudolf Triebe from DLR. Enjoy his talk.
Thank you, Rebecca. Thank you. I'll try to connect this here. This is the computer here? Yeah. It seems to work. Yeah. Okay, yeah. Welcome also from my side. Thank you for having me here at the workshop. And yeah, I'd like to give my perspective a little bit from the side of robotics, but from the particular side of robot perception. And I'd also like to give you some kind of introductory about what generative models in general are, where they come from, how useful they are, what kind of models are around there, right? It's not just the one that we most often know. There may be many others. And then also how we can use them and how we can leverage actually them for perception. But before, I'd like to start with kind of some introductory slides. What is perception in robotics, right? So what do you mean by that? So you have this robot, and the robot has to do certain tasks in the environment, and the first thing it has to do is it has to perceive its environment and answer certain questions, right? It sees something in front of it, and the first question is, what is that, right? And this question is already quite difficult because you could say, well, it's a table, right? Of course, it's not a table. It could be a table, it could be a banana, whatever. But the first question is already hard to answer because it depends on what you actually mean by that, right? So that could be something in front of it, and that's already a difficult thing. So, and usually what we have is you have some kind of like selection of different possible classes that you can see in front, right? But you can see already the one big problem is here that very often we don't want to restrict the system to have only a fixed number of classes, right? There might be an unknown number of classes around, and that's what we call the open world problem. We don't want to restrict and say you can only have four classes, table, chair, couch, banana, but there should be an unknown set of these classes. And the second thing is, of course, if I want to interact with this object, then I need, of course, to know its pose, right? That's the next step. And the second and the last thing is, third thing is, I need to have some kind of idea how to grasp it, right? I need to place the finger around this object and then have a grasp of it. This is the whole topic of perception, well, at least for manipulation. And there's this typical, classical ways of doing it. So first of all, you detect the object, right? For example, you have these kind of typical AI-based learning techniques that give you a bounding box around the objects and tell you where they are in the image, right? But then once you have that, you have to, sorry for the video doesn't play that easily. But in addition to that, you can now find the pose, right? You have this cup here, and this is the estimated pose of the cup that tells you exactly how to where the cup is and how to grasp it. But you can also do that, of course. Sorry for the. With a different technique called tracking, right? This is shown in this video. Does it plays? I hope. No, it doesn't. Anyhow, it doesn't play. Where you can just do this frame from one frame to the other one and use a tracking technique here. And the last thing that you want to do is grasp detection of grasps, right? You have a robot here that sees the environment in 3D and then performs the grasp and executes it. Now, as we all know, the modern approach to do that is using deep learning, right? This is a very rough schedule of how this looks like. Before we had very little, like many steps in between, feature extraction and so on, classification. Now we do this all in one big algorithm, right? We have some network that has parameters P and some image, and we just go from input to output, right? This is proven to be works much better because if we have enough training data and so on, then this is a nice and good approach and proven approach. And some example of doing that in a different kind of context, but similar in the idea is you can use this kind of so-called autoencoders to learn representations, for example, in this case, of orientation, right? You learn the orientation of this object instead of using old school stuff like Euler angles or rotation matrices or stuff like that. You just let the system learn what the representation is for orientation by just showing it different inputs that map to the same output, right? So you show it input images that have different shifts and different scales, but they are not different in orientation. And by that, the network implicitly learns what orientation is and you just don't care about what your representation of this orientation is, right? So this is this general new idea of just letting the system learn and letting it represent its own representation. Now, where does the word generative now come from, and why do we have generative models? So traditionally, there were at least two kinds of approaches to do these kind of learning techniques. There was this discriminative approach and the so-called generative approach. And generative approaches are actually not very new. They seem to be new and seem to be a nice and hot topic, but they have been around for many, many years already. Still, there was not yet the deep learning approach for it, right? So the classical way of doing, for example, classification is you have some input data, right, some images, and you have some output data. And this could be just classes. And this is the thing that I showed at the beginning. You have n classes and only of then n. And all you want to do is now learn a mapping between this input data and this number of integer numbers of classes, right? And the classical way of doing it is the so-called discriminative model, right? Where you learn a posterior, right? You learn a model that gives you a posterior distribution. It's basically a probability of some class label given some input data. And with that, you can do classification then. And so far, this was a very good working approach. But the problem with that is, and one of the problem is, it has problems with this open world problem, right? So if we cannot specify the number of classes here, if we don't know how many classes there are, then it's hard to use that model because it can only distinguish, and that's why it's called like that, class A from class B, but it's not able to generate new samples, right, from a given distribution. And this is this different idea, right? So you have, here you have a different approach where you say, let's generate new data from a given distribution X, right, which is the opposite of this one here, right? And then you can use that for classical ways, for example, in Bayes' rule, right? You just turn this around, say, okay, I have this distribution here. I can now multiply it with the class probability, right? I can say how likely is this class, and then can have exactly the same reasoning as before, but now with a much more fundamental approach. In the history, these generative models were always more expensive, right? And today this shouldn't be a problem, right? You have much more better computers, and so the idea is now, how can we extend this generating new data idea into some new algorithms? And this is the basic principle of what generative models in total do, right? So basically you have just this representation here. You have a large data set. It could be your data, your images, your whatever, your sound, whatever you have, right? This is this X data set, which is very hard to handle. It's very high dimensional and very hard to represent, right? You just have this given as training data, for example. And now the main idea of a generative approach is to learn a function that samples from an easy latent distribution Z, right? And maps that latent distribution to the data distribution. So G is just a function that has a parameter theta, and all you do is now we adapt the theta parameter such that the G of Z is very similar to X, right? So you just resemble the given data that you have, right? And then what you can do is you can just sample easily from Z, apply G, and you get new data that looks like your training data, right? And of course, what that means is you need some kind of similarity function that tells us that what you sample here is actually similar to the true data that you have here, right? And the better that works, the better you can generate new data, right? And one of the first approaches to do that were GANs, right? They actually had a generator here and a discriminator here, basically a nice combination of the two, where you generate first, and then the discriminator shows us or tells us how close are we actually to the true data, right? And then you can do things like a new data sample can be then computed, and how likely is that? Well, you can, if you do this in an efficient way here, you have the similarity here between your latent Z and your data, and you can do this with this integral and then compute the so-called sample evidence. Now, why is this good? Why do we do this? Well, first of all, it's of course a very good test to do representation in high-dimensional data, right? So if you can generate new data, then I can use that data and see what happens if I do training learning with it. And if that works well, then I have a good indicator that this generation or that this distribution I generated is the right one, right? This is actually a quite nice way of doing it. Another good reason is, for example, in reinforcement learning, what I need is generative models. I need very often something that tells me a potential future, right? That samples things into the future, and that can then be used to do learning, right? I try things out and say, what could be the potential future? And generative models are very good at that. We can use that to train with missing data, for example. We can use semi-supervised learning. We can work with multimodal output, right? Multimodal output means that for a given input, for example, in a sequence, a reading sequence, there are many possible outcomes, right? And classical methods cannot predict all the kind of outcomes, right? They usually just give you one most likely one, but it's probably not the one that you want, right? And generative models can give you different kinds of outputs given a certain input, right? They can generate new possible outputs, which is a very nice property. And of course, it can be used for tasks that require good samples, for example, hyper resolution and stuff like that, right? Whenever you need new data sampled from a given data set, then generative models are the approach that you want to do. Of course, there are also some challenges. I think this is something we should also discuss probably later in the round, maybe. So first of all, of course, we have this inverse problem, right? So uniquely finding this distribution is impossible, right? Because if you have a given training data set, there's many different distributions that might fit to that one. That means you have to find hyperparameters, you have to find the right architecture, and so on. Another challenge is that we need to compute the similarity measure, right? If you go back to here, then you'll see that having this similarity measure, where is it? Is not that easy, right? And the question is how to do that, right? So this thing here, right? And there's two ways basically to do that. Either we have some kind of, again, as I told you, a discriminator that learns the similarity, or we have a generator that is invertible and then can do this in the latent space, right? We can just invert the data and then do the comparison in the latent space. And of course, the next problem is which is the dimension of the latent space, how long is it, how strong is it, and so on. And another problem is, of course, the latent space. If it's a very simple distribution in latent space, then it might not be sufficient to actually generate the data that I need. So this is a collection of generative models that are around there currently, and I have to say currently because this kind of zoo of methods is growing quite fastly, right? And most of us may know this one here, right? GPT, of course, but there are many, many others, right? Again, the GANs were the most known ones years ago. The VAEs have been also around for some time, and now newer things come up. For example, autoregressive models, normalizing flow, diffusion-based models. These are techniques that are used a lot also in vision. And I give you very quickly two examples of the autoregressive model and the normalizing flow. This is an example where you can learn or train a model to generate potential poses of a robot gripper, right? So you have a hand of a robot, you can see this here, that has to grasp a certain bottle or an object. And what you can do here in this approach here is for a given object, you generate with a special kind of model here, potential positions in X, Y, Z, and in the quaternions here. So you have 7 parameters that you sample from. And then, yeah, after that, you can then test which are the good joints for the fingers to actually grasp that object, right? Again, this is a generative model, and if we compare that to the other generative models that are around here, this is the Wasserstein-GAN and the VAE that I just showed you, then the autoregressive model in this case actually works slightly better because it doesn't intersect with the object so much and so on. And we have here also the numbers that tell us that this method actually works quite well. You can see here some results how to actually grasp objects with this method. And very quickly, the last thing is this normalizing flow. I told you that when I generate data, an important question is how can we do this similarity computation? And one idea here is to actually have a generator that is invertible, right? So we have a so-called diffeomorphism that can be inverted, and then you can do things like doing comparison in the latent space. The way this looks like is here. So you have this data space, right? This is your data space that you start with, and what you learn is a function that goes into some latent space, which is easy to sample from, right? This could be a Gaussian, and then you can just invert that and say, hey, if I sample from that, I invert my generator, and I get this kind of samples here, right? So this is the major idea. Of course, the problem is if this is not multimodal, right? So how do you do that? And this work here will actually try to find better base distributions that are not simple Gaussians. So we can do this multimodal base distributions and match the topology of this to the topology of the input data. And by that, you can then do things like OOD detection, right? Out of distribution detection, the thing that I told you in the beginning. We have this open world assumption. We don't know that certain objects are around there, but the model can now tell us that it doesn't know this, right? So it can tell us this is something new. I've never seen that before. Because I can generate things, I can use a generator. and then say, well, this new data set or data sample is something that I cannot generate well, so that must be something new, right? So the approach of generative AI here actually helps us to be able to tell what we know and what we don't know. So coming to the conclusions, I think robot perception, I've told you, is mainly concerned with these major tasks, right, that I showed you, especially pose estimation, but also graph detection. The generative approaches that we have shown here, they can generate new samples, and they're conditioned on some training data, right? And I think it's important also to know that there are many different approaches, and if you look at the literature, they're growing, and yeah, again, we don't know if in a couple of years there will be even more, right? So this is quite a very fast-growing domain, and which is actually quite exciting. I've shown you two examples, right? Autoregressive models and normalizing flow. And I think the last message I'd like to convey here is that these are very promising, but there's a lot of research yet to go, right? There's not yet the one generative model that solves it all. It's not there, right? We cannot just talk as generative AI as the tool that solves it all, right? It's a domain that we want research on, and there's many techniques that we like to find and do, but we cannot say, well, now we have this and we apply it to everything, because many things we don't know yet, right? So it's still research here, I would say. And with that, I thank you.
Thank you. So, and the next talk is from John. He is from the University College of London.
Correct.
Right. And yeah,
Thank you.
the floor is yours.
Okay, thank you. Thank you for the invitation. And difficult acts to follow, really impressive and interesting talks. What I wanted to focus on was the question of where human-centric AI sits with regard to the generative models revolution, if you like, that we're seeing. And really, I would like to envision a positive application of large language models. I'm calling them large language models, but I'm thinking, large generative models of any sort, multimodal, as I will argue, we will, need if we're going to really realize some of this positive vision. So just to sort of set the scene, human-centric AI is really, I think, in my view, at the center of the European vision of a positive role for AI. We've talked, this mention of various sort of ethical AI, responsible AI, verifiable AI. All of these terms, I think, are captured in this idea of human-centric AI, which is really setting a vision that AI empowers humans to be more effective, more creative, and have a deeper understanding of the topic or the environment that they're working in. And I believe that is actually a really good vision to have, but I think it's one that we haven't uncovered enough, in that I think a lot of the sense of talking about human-centric AI is only scratching the surface of what's really required to deliver this deeper vision of what would be required to really enable humans to have the benefits of AI in the way that will enhance our real understanding and experience. So I believe there's a lot more that we need to think about on that topic. We in the HumanE-AI Network of Excellence have spent quite a lot of time around this topic. It's been the focus of that network. And the question I wanted to address today, how do LLMs impact this research vision? Is it now obsolete or supercharged by the emergence of the large language models? So I'm going to just start by linking to the HumanE-AI research agenda, which highlights the ingredients of collaborative intelligent systems. And again, this is where I think, the scratching the surface, it sort of talks about, well, we need AI to be supportive and help people do what they want to do. But actually understanding how that can be achieved requires really quite complex problems to be solved, particularly this issue that was raised by Paul in his talk at the beginning of finding a common ground across a range of levels for communication to enable effective cooperation between an AI system and a human. Within the research agenda, there were a number of levels identified that roughly correspond to different styles of collaboration, with collaborative systems potentially involving more than one level. So I'm not going to delve a lot into this, but just to show this diagram that sets out the levels from the kind of lowest level of reactive, which you might, probably the best example if you've driven a car with a lane tracking system. If you deviate from the lane, it kind of pushes your steering wheel in a reactive way to push you back into the lane. Of course, it might cause you to run over the bicycle you were trying to avoid, but that's another issue which might be solved by the situational level, which would have an understanding of the context within which this particular AI system interaction was happening, and would we've seen examples of that, particularly in the robot talks, which I think were very inspiring in the way that they were able to understand the context and bring that to bear on the particular AI task. Operational is about how to actually plan. Again, that was very relevant to the robot talks, but I think is very much also relevant in terms of thinking about planning for a human getting greater understanding of the potential impacts of their actions and decisions. Practical is actually learning skills, either one from robots to human, or from AI systems to humans, or from humans to AI systems. And the final level, creative, is around what we would think of as a genuinely, let's say, deliberation between an AI system and a human, in which ideas are shared, but also feedback is taken in both directions. So the AI system is learning from what the human is saying, but also the human obviously is potentially learning from what the AI system is giving. So this just to give you kind of an idea of the different levels and complexity of this framework of trying to understand how AI systems and humans can constructively interact. So just to mention some of the ingredients that I believe are essential for realizing human-centric AI, fluid communication that facilitates the aligned representations that are necessary. And I don't think we can envisage those being set once and for all, even for a fixed particular topic of communication. Any human has different understandings of different topics, different words are used differently in different contexts. We need to continually realign an understanding, as we do when we communicate with another human being. We're continually checking to see whether what we've said has been understood in the way it was intended, and if not, hopefully try to correct for that. And as Paul so eloquently emphasized, we need the link to the real world. Proxies such as Wikipedia are not enough. We need direct interaction with the real world through the appropriate sensors and other modalities. What LLMs definitely bring to the table is this fluid verbal communication, but they lack grounding and links to appropriate ontologies, which again can lead to the hallucination problem that we've seen. So one of the things that the HumanE-AI-Net has done during the final year has developed a number of so-called macro projects. The micro projects were mentioned earlier this morning, but in the final year we focused on a smaller number of macro projects. And one was looking at linking large language models and logical reasoning. And I just want to say a few words about it just to illustrate where I think some of the potential and let's say stress points are. So this is a system that is attempting to enable a lifelong learner to access educational resources or information that would be open online. And the idea is to try to move away from what would be a more classical recommender system, which is really what's illustrated here in the upper part of the diagram, where the AI system is trying to understand a potential need and makes a recommendation. And the only point at which the human can interact with that recommendation is to either reject it or accept it. And what we want to move to is this augmentation of the decision process by which that recommendation is made. And that's the lower half of the diagram here, in which the human and the AI system collaborate in order to understand better the need, the human need, what they're interested in, perhaps assist them in understanding the context of that interest, what that interest might cost them in terms of effort, and then making appropriate recommendations in a sequence that would lead them to the goal, educational goal that they were aspiring to achieve. And this is sort of a breakdown of how the system is currently configured. So there are a number of elements that are interacting. The large language models are this section on the bottom right here, particularly in terms of enabling that fluid interaction, but they are translating always the input from the user into a logical framework that has been developed in terms of understanding the ontology of the area of interest that the user is wanting to study, so that we have that kind of relationship between a more fluid interaction with actually a more logic-based description of the topics. And we believe that that's possible when we have a limited domain. So this would be always developed with reference to a particular domain of knowledge that might be of interest to the user, rather than a global ontology or attempt to create some understanding of all of knowledge in that sense. And that then provides this potential for adjustment to find the common representation that will enable the user to understand the context and then make an informed choice about the particular topic or video or material that they might study. The further interaction up here is more reinforcement learning in terms of trying to understand how they're progressing from understanding their interactions with the material. So that's just to give you a kind of example where I believe, we can see the role that large language models can take in kind of taking human-centric AI to a new level. Clearly, multimodal data can play an important role in enabling situated communication with humans, but we should not consider LLM technology as finished business. I'll switch that on if that's okay. And I think there are several areas in which we really need to see quite significant advances. Particularly attention models may need to be adapted for different types of data and tasks. For example, edge computing may require more complex techniques for focusing attention than the simple linear heads of transformers. So I don't think we should consider this technology as somehow closed off and finished. An example of Kolmogorov-Arnold networks seem more efficient at learning sensor analysis than physical. Training of deep learner transformer models may benefit from innovation. I'll just give two quick examples of that. One is in applying LLMs to modeling the immune system, in which additional constraints were added in order to appropriately train the models with the language, the normal language training objectives not being strong enough to focus the attention. And this developed system, SEPTA, showed clearly outperformed more standard large language models such as PERT and more traditional distance-based. I think the other thing we should think, out of the box in terms of how basic gradient descent can be improved, and a theoretical analysis of how best to generalize from a batch motivated a much more efficient use of data, as shown here in training a deep network with CFAR. performance reach the level that was achieved by a standard stochastic gradient descent after 70 blocks after just something like 3 or 4. So I think there's a lot to play for, is what I'm saying, in terms of getting inside the box and understanding how these things work. Other potential advances in LLM technology, federated learning allowing decomposition of objectives, and more focused distributed learning, introduction of invariance is appropriate to different domains. I mean, the CNN technology is really natural for vision, but not necessarily natural for other domains. Training enhanced by domain knowledge. This is referring to the introduction of physics-based models. Data-centric engineering is showing very impressive performance for building in knowledge from physics, like the Navier-Stokes equation. Really amazing results, which I think we can really bring to bear. And understanding how different attention mechanisms work in different contexts would enable efficient engineering of more complex models in diverse domains and applications. So just to conclude, I think LLM technology has proved a game changer, without doubt. It should be viewed as supercharging the European vision of human-centric AI rather than replacing it. And human-centric AI can be advanced through LLM extensions. I've given the example of the true reason system, demonstrates grounding in logical reasoning, the use of multimodal data, extensions of transformer technologies such as enhanced attention models, and extensions of deep learning technologies such as enhanced invariances and learning methodologies. Thank you.
Thank you so much, John. So now you've heard from them. What do they think they would use the money for? It's time to hear from you. How and what would you do with the funds? Give me a second. What do you see? Okay. Get your mobiles out, scan, and let's start. And if someone doesn't have internet, there's a network literally called internet. It doesn't need passwords or anything. You can log in that. Let's get a feeling of who's actually in the room and who's on the hybrid, who's online with us. Thanks a lot to Agnes for helping us moderate the online part, and Nico. And she will share the Mentimeter in the online chat. So our online audience as well can contribute. And you can choose different, like you can choose multiple things if you're belonging to a couple of the networks at the same time.
We are using vision here.
Oh, yes. Can you add it to the Taylor, to the NOE's one, and then I will add it? If you're in vision, add it to number 1, and then I will add it afterwards ad hoc. Okay, anyone still entering stuff? Okay, so it looks like the majority of our audience today is from the first round of the NOEs, and we're having a lot of people as well from everyone else, so thank you for being here. Now, we've noticed that genAI means different things to different people, so try to explain what is genAI to you in a single word, and let's see what comes out. Scan. Okay, that's quite positive, that's nice. What else? Okay. genAI. Surprise, that can be positive and negative. Creation, opportunity, tool, world model, democracy dead, nice one. It's gonna save our time, it has a huge potential. So seems like the majority, Swiss knife, that's a cool one, you can do a lot of stuff with that. And it's very fast moving indeed. Okay, so the majority seems to be very positive about it. Last 10 seconds if you're entering what genAI means for you. Anyone still entering something? Okay, we move to the next one. If you can choose 2 application areas to apply GenAI in them, something like health or music or whatever, which ones would you choose out of those? And just in case you're wondering where are those coming from, this is what's a summarization of what's in the call for funding from the European Commission. That's why we wanted to get a little bit of feedback about that. "20 seconds remaining. Keep voting. Keep your votes coming. "10 seconds remaining. Come on, we need to work under pressure. Afterwards, you're going to have lunch, so. Anyone still voting? Our online audience, is anyone still voting? If you are, say something in the chat, and then you can see this. Okay, so it seems like the majority wants to use it in health, and they think this is what's going to get the next breakthrough for Europe. Digital industry as well, and climate and energy mobility. These are like the top themes with interest across the other things. Now, if you have 50 million euros, what GenAI research challenge would you want to look into? You have 1 minute to think about that. And you can start entering your questions while, your answers while thinking, and we're going to vote on that as well. Is anyone still scanning the QR code, or can I close it? Anyone still scanning? Okay. Semi too late. Okay, what you can do is go to mentimeter.com and enter the use code up. Do you see it? Okay. The number up. Okay. Sorry. We're getting a lot of stuff. Causality-aware GenAI, end-to-end social human-robot interaction, robot manipulation, reducing consumption, learning models to effectively improve agents, robots, make it more robust against abuse and bias, lower source GenAI, climate change, real world, optimization diagnostics. Is anyone still entering stuff? Foundational 3D vision models. Because I'm going now, like once you're done, I'm going to group them using the magic of AI, and let's see what themes are coming up, and then you vote on them. Anyone still entering stuff? Okay. Let's see what the AI thinks the themes are. So the first one is the human-robot interaction. The second one is ethical AI. The third one is related to the generative models themselves. And the fourth one is related to robotics. We have healthcare and causality research and environmental impact. Now, I'm going to open this for voting for you. Unfortunately, the voting doesn't come with the categories, so you need to vote on specific items, and you have 2 or 3 votes. Vote. What resonates the most with you? Anyone still voting? You have 10 seconds. Come on, pressure, food. 5 seconds. Okay, let's see the results of our votes. So human-robot interaction and ethical AI seems to come as the most popular in terms of ideas. Now, the last one. Turn to your left, talk to the person next to you for the next 3 minutes, try to come up with the next big idea for 500 million euros. 3 minutes counter, start. Talk to the person on your left. If you can find someone on your left, talk to the closest person you can find and come up with an idea. Hop, 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 fast. Talk to someone and get ideas. You have 3 minutes. And don't be afraid to be loud. It's okay. The room is good. And for our online audience, please discuss in the chat. And we're moderating that somehow. Yeah, don't keep it on. This is okay. No, keep it on. That's fine. Talk with the people and discuss, because we will also do voting. So let's see, what should we do with the 500 million euros? "30 seconds remaining. "10 seconds remaining for entering your answers. 10 seconds remaining, our online audience. Okay. Is anyone still scanning the QR code before I do it again? Anyone needs the QR code? Let's call. Okay, there is a lot of stuff coming up. 5 seconds remaining, then I will group them using AI. So we're having physical AI, models that can self-improve and evolve through interaction, breakthrough in medical research, reasoning and low-resource AI, health again, AI for science, sports AI, human-robot interaction, energy-efficient training, genAI on the edge, investigating novel approaches for the models, quantum computing, agents, and edge again. Let's see. So seems also the concentration is on the human-robot interaction and the physical AI, and then self-improving the models and edge AI, social understanding, health, quantum computing, breakthroughs, and miscellaneous. And with that, we'd like to thank you so much. Oh, actually, you need to vote. Last thing. And then we will thank you. 20 seconds remaining between you and the lunch break and the results. Ten seconds remaining. Enter your last vote. And so the human-robot interaction and the physical AI. And with that, we'd like to thank you so much for having us today. And please enjoy your lunch. See you.